Welcome to the Randomizer for February 2nd, 2022. I'm Charles Schultz, your host, and tonight we're going to have a wonderful discussion of an unusual term, and I have to tell you the story behind this after I show you the term. The term is Siegbahn, and I have never heard of this before, and so when I ran my randomizer program to choose the topic for the show, two copies of this name popped up. And I thought that's unusual. There's 1,621 terms in my list, and the chances of picking the same term twice, as you can see, is very small. But what is most interesting above and beyond that is that when I looked into it, there are actually two people named Siegbahn who both won Nobel Prizes. And so we'll get into that in just a moment. I encourage people to join our weekly lessons that we present every Monday. We're doing a course on meta world right now, and we're talking about the ascent of humanity from sticks and fire to nanotechnology. Go to the site, click and sign up for that. It's a great, fun lecture, very informative, runs an hour with a discussion time afterwards. Every Monday for the next 5 weeks, this class will be continuing. Our second lesson will be starting Monday. Also, if you have an opportunity, go to schultzlaboratories.com or universesciencecenter.com and sign up as a member. Join us, help us expand and grow, add more material to our galleries, and get your Oculus, walk around a little in the virtual world there and see what you see, and give us some feedback. I'm sure you're going to enjoy what you see. So let's get back to the subject at hand, Siegbahn. There are two Siegbahns, as I mentioned, and so I just couldn't pass up on what an amazing coincidence or opportunity this is. The first was Carl Mann-Jorg Siegbahn, and his early work was in X-rays and in, well, basically spectroscopy. And in a spectroscope, you look at the spectrum produced by something that is heated or energized in some way. Spectroscopic analysis is where you literally heat something up with a flame until it glows, and then you look at the signatures of light, and you can tell from the spectrum what it's made of. So think about it. Every material we have glows in a certain way based on what it's composed of. And it's almost as if it has a fingerprint in light. And much of that light is not visible to the human eye. Part of it was in the infrared spectrum, quite a bit of it usually. And in the years past, I used to help repair infrared spectrophotometers, one of the things I used to do at a job I had then. Some of it is in the ultraviolet spectrum. But beyond that is, of course, the X-ray spectrum. Now, Siegbahn the senior did a lot of work in the X-ray spectrum because it has an interesting effect on matter. His work looked directly at the effect the electromagnetic force has on matter. Photons have momentum. They are momentum. And when they strike something, they can cause it to emit other photons. And you can learn something about the emitted photons and therefore about the composition of the material itself. So the X-ray spectrum is extremely useful for identifying samples of materials and analyzing them. Not just taking an X-ray, a picture of it, but literally understanding its structure by the fingerprints of light that it gives off in the X-ray spectrum. So his interest showed that you could get X-rays from atoms by changing their paths rapidly. So if you have an atom that's very energetic and it passes by, well, I should say an electron. Electrons are negatively charged, and that electron is moving rapidly, and it goes around a positively charged proton in a nucleus somewhere. As it changes velocity, it spits out a quantum of energy, a photon of X-rays sometimes. And this is the whole point, X-ray emission of a photon that's come to a rapid change of velocity. Now, if you ever had an X-ray, you wonder how they make the X-rays. It's actually very simple. They have a high voltage tube that emits a beam of electrons, and the electrons slam into a metal plate at the end of the tube, and when they do, they come to a halt. Well, in doing so, through the metal is a stream of emitted X-rays. This is the standard way of producing X-rays. So his research showed him how to emit these X-rays, how the effect works, and he received a Nobel Prize for his work in X-rays, fluorescence, and basically analysis, microscopic analysis using X-rays, spectroscopy in 1924. So it's interesting because Swedish physicist, Nobel Prize, analysis of energy and matter, and then his son, Kai Siegbahn, took up the work and kept moving with it. Now, it's understandable. If a family is intelligent and driven and they have interest in the same subject, or if you're exposed to that subject matter as a child, it's pretty clear you're going to learn something about it. And it caught his interest as well, his son's. So his son worked with, and come to now, let's get right to the point. This is the interaction of a force and matter, and it's very fine control. And his son studied this, and he found that X-rays could be used to identify materials, the compounds, not just the elements. And this is interesting because everything is about electrons. In chemistry, everything is held together by electrons. And those electrons, when kicked off of an element, will tell you how much energy it took to leave the orbital, the little spot around the atom the electron appears to live. Well, there's a thing called work function, and it is so much of the energy removed, so much left over, and the electron has a path and a momentum as a result. But photons are very powerful, and even though they aren't solid objects, they can have an influence on matter that's pretty amazing. Think about it. You've seen the sunglasses that darken on the exposure to sunlight. Well, this is because of the presence of ultraviolet. And ultraviolet is one step below X-rays on the spectrum. So if you looked at it, you have infrared, you have the visible light spectrum, you have ultraviolet, and then you have X-rays up beyond that. So it's a progression, just as the octaves on the keyboard of a piano would be. Our octave, the visible, spans literally one octave. There are about 5 octaves of infrared below it, and about 2.5 octaves of ultraviolet above that. Now, some will say up to 5 octaves, and I won't argue with them. As physicists, they know what works for them, what is utilitarian. So they could be right. And for some, they'll say you're just quibbling between the definition of ultraviolet and soft X-rays. But it's not really an argument that's worth having. We simply know those photons exist, we know what their energies and spectrum are, and how much utility have. So what's interesting is his son, Kai Siegbahn, went on to develop means of scanning an electron beam over a substance, measuring the angles and energies of the electrons produced, and determining something about the subject. For instance, the composition of the material. Now, it's easy to identify an element when you're analyzing it through X-rays, but how about a compound? His reflected particles coming off of this sample are capable of determining how they were bound together in a compound. And this gives you a fingerprint that allows you to identify the compounds. Now, why is this important? Well, this is the fellow who developed the electron spectroscopy for chemical analysis, or ESCA, which is the standard method of measuring the contents of air pollution particles. And it's also extremely useful for measuring the materials on catalysts in industrial reactions. For instance, a catalyst sometimes, now what a catalyst is, first of all, it's a compound that is not used up, or it's a material that is not used up in performing a chemical transformation. For instance, some catalysts are very good at breaking ammonia down into hydrogen and nitrogen, and sometimes it goes the other way. There's another whole fascinating story right there. But a catalyst isn't used up. However, sometimes they fail to work properly, and you have to understand why. This method of X-rays allows you to analyze the surface of the catalyst and find out what's stuck to it, what's the contaminant. So the contamination can be understood, remediated, and the catalyst put back in service in many cases. And believe it or not, one very important catalyst is made out of the metal nickel, and it's called Raney nickel. They invented it by dissolving nickel in molten aluminum and making a compound of the two. Now, what's interesting is they really don't like to mix really well. One is quite dense, one is very light, and chemically they're not real friendly, so to speak. So, rainy nickel is made by stirring up a sample of aluminum and nickel and letting it solidify, and then etching away all the aluminum with something such as sodium hydroxide, which is known as lye. It will dissolve the aluminum readily, and then after being washed away, you have an incredibly surface area oriented material, a lot of convolutions, it's like a rug rather than a sheet of paper. And so rainy nickel provides a huge active surface and acts as a catalyst in many chemical and industrial reactions. So this is a means of analyzing that surface. And when I talk about a surface, you think, well, yeah, like a layer of paint or the surface of a mirror where the light is being reflected. We're talking about a surface of only 5 nanometers. Now, how big is a nanometer? Well, a nanometer is 1/1000th of a meter. So if you take a meter and you break it up into 1,000 pieces, one of them is a millimeter. And you know how big that is, about the thickness of a pencil point or a pencil lead. So that would be about a millimeter or so. That's a little big for a millimeter. If you took a millimeter and you divided it up into 1,000 equal pieces, each one would be a micrometer, 1/1000th of a meter. And if you took one of those micrometers and divided it up into 1,000 pieces, each one would be a nanometer, 1/1000th. 1 times 10 to the minus ninth, you got 9 zeros after this thing. 1/1000th of a meter is a nanometer. What can you compare it to for size? Believe it or not, the hydrogen atom is literally almost exactly 1/10th of a nanometer. So 10 hydrogen atoms packed end to end would be about a nanometer. His analysis method allows us to see things in layers as thin as 5 nanometers. That's pretty powerful analysis. And it allows you to do some extremely subtle investigation into systems that aren't working properly. Or if you have a new material you're trying to understand, this can give you the signatures that tell you exactly what it's composed of and how. So this is the importance of it. Our world is made a better place because this technology allows us to analyze things and get definite answers like right away. And right now, if you look online, you'll find that there are some amazing tools appearing using X-rays and giving you the chance to take a sample of a metal, place it up against it, and it'll exactly identify the alloy of that metal for you. And they're not very expensive. We're seeing some pretty magical looking tools appear now based on X-rays. So, Siegbahn, an amazing pair of individuals, father and son. The former won his Nobel-prize in 1924 and the latter in 1981. And finely focused X-rays. Read the properties of the material, get decoded into an answer, and you've got it right there. So I hope you like the subject matter. We'll have a new random subject tomorrow. I'm going to take any questions if anybody has any about the subject matter. The floor is open. I see a number of participants in our live chat tonight. Feel free to ask any questions you have about whatever. And meanwhile, I'm going to go ahead and say I encourage you to go to our site, sign up for our classes that occur every Monday at 9 p.m. Eastern Standard Time. And the randomizer is every weekday at 6 p.m. Become a member of the Universe Science Center or of Schultz Laboratories. It's the same organization right now. You'll see some changes in the near future. I'm going to make it very simple. Become a member, help us expand and add more content to our rooms and explore our virtual worlds we have in there. Sign up for our classes, support us and our growth. And I thank all of our supporters we have right now. It's been amazing what we've been able to achieve with some followers and supporters. So please, floor is open for questions.
Yes, hello, Charles. This is Elizabeth.
Yes, please.
Yes, I'd like to know, it was very, very interesting, Siegbahn. If this technology was used, what would the vision of a new world look like?
Well, it's such a good general purpose analysis tool for, and not biological material unless you're going to destroy it. It would knock a few atoms apart in the process. But overall, it's excellent for analysis. They literally are making devices that you can carry in your hands that can analyze air pollution, content, contaminants. Similar studies can be done with small samples of water. It allows us to find out what's contaminating an area, and that's the first step to finding out how to fix it. I also know that in many cases, when you're trying to find out what sort of a non-organic toxin is present in something, this could allow you the ability to analyze it. What's particularly useful is the identification of metals, because many times it's very difficult to tell what sort of a toxin has influenced something if there's only a trace of it. But it only takes a few atoms of certain metals, such as lead or thallium or bismuth, or, I can name a number of them, chromium, for instance, to be in a system and act in a toxic manner. So this is an excellent means of analysis, and it should be readily available everywhere very shortly. The way the technology is advancing these days, things are becoming very compact and very easy to use. So I would say, first and foremost, it's one of those tools like a magnifying glass or a camera that allows you to get an image of what's going on and then decide what to do about it. So, anybody else? All right. Well, I appreciate everybody who has participated. I found something that I found very interesting when I was putting the show together. And, I am a reader of the Bible, and I see things that sometimes stick in my mind. And 2 Corinthians 4:18 says, "As we look not to the things that are seen, but to the things that are unseen. For the things that are seen are transient, but the things that are unseen are eternal." That's a fascinating take on things. And somehow for me, it actually seems to represent a little bit of what both Siegbahns were working with, unseen things that just don't go away. Electrons are going to be around for the age of the universe. Photons will be around for the age of the universe. And it may not be a technical verse, but it certainly seems to resonate with the subject matter. So I would say that this is the randomizer for the 2nd of February, and it's been an interesting one. And we'll have a new segment for tomorrow at 6 p.m. Please join us. That's Eastern Standard Time. And thank you for everyone for showing up. This has been a lot of fun. Have a wonderful evening and make the world a better place.